and I think we will come to the next presentation from Francesco Gini, so that we can have more time for the afterwards open discussion and the final remarks. So Francesco Gini is also working at the Navigation Support Office at ESA ESOC, and he will give a presentation about the Galileo precise orbit and clock determination and POD concept at ESOC. Francesco?
I'm here. Let me quickly change the screen. Okay. Can you tell me if you can see the screen and you can hear me correctly?
We read you 5 by 5 and can see the screen.
Okay, perfect. So thank you for the introduction, Werner. So I'm Francesco Gini, and I will be presenting today the Galileo precise orbit determination and clock determinations and the POD concept that we have at ESOC. And this presentation will be on behalf of the entire navigation support team. And most of the team is also connected online to this meeting. So I will spend some words on who we are. So we are the Navigation Support Office. We are located at the European Space Operations Center, ESOC, in ESA in Darmstadt in Germany. And we were one of the founding members of the IGS. And since more than 20 years, we are involved in multiple applications of the POD concepts, mainly focusing on the Galileo constellations. So as my talk will focus today, also our activities will focus in general on the Galileo, in particular covering different aspects of the Galileo POD. And we generate routine Galileo precise orbit determination products that are also published on our website, and we also contribute to the IGS with these products. And we focus our activities in the models development that range from satellite orbit dynamical modelings, and also we perform attitude and clock modelings. We also generate special sets of orbit and clocks products for Galileo for scientific analysis and applications. This was the case of the GREAT project to demonstrate relativistic effects on satellites. And we provide further analysis for Galileo, such as metadata test and validation that was kindly presented also by our colleague Francesco Gonzalez in 2 talks before. And we also do analysis on the clock performance of the different Galileo satellites. So how we perform the Galileo precise orbit and clocks determination at ESOC. Our process is based on batch processing of daily arcs based on the dynamical POD approach. And we believe that the most important aspects of the POD related to Galileo, but also related to other GNSS processings, are the quality of the signals, the quality of the satellite modeling, and the quality of the stations and the network geometry. With respect to the quality of the Galileo signals, we have already seen in previous presentation from our colleagues the excellent performance on ground. And let me also add here that we have also demonstrated in the last years the excellent quality of the Galileo signals in space, thanks to the Copernicus mission Sentinel-6, which was one of the first ones tracking Galileo with very high accuracy in order to do POD on a satellite in space. With respect to the Galileo modeling that we do at ESOC, we understand that one of the main drivers in the Galileo orbital error modeling is given by the high area to mass ratio, which means that the satellites are very, very light and have big dimensions, particularly the solar panels are pretty big. And if we do the ratio between the area of the satellite and the mass of the satellite, we end up, as like you see here in the table on the top right, with Galileo FOC being one of the top ranking with based on this ratio, which means that we have to be very careful with the modeling of this satellite, because this makes the satellite very sensible to the radiation pressure effects, solar radiation, earth radiation, and thermal radiation effects on the satellites. And we believe that the models that we have developed so far, based, for example, on the public metadata that were presented, are very good quality. But what we are doing all the time is trying to continuously improve the quality of these models and hence the quality of the products that we generate. I'm showing here at the bottom 2 typical, let's say, approaches for POD application, how we model the satellite. On the left-hand side, in the picture below, you see the box wing model, which is mainly consisting of the box, which is the bus of the satellite, and the wings, which are the solar panels of the satellite, where we apply geometry and optical and infrared properties to it to model the satellite. Or we can also do more advanced and sophisticated techniques like ray tracing techniques here that is shown on the right-hand side. I was talking before of the importance of having a nice, an excellent, very good quality network of stations. And here at ESA in general, but also at ESO, we are maintaining and operating the ESA GNSS observation network, which is called EGON, which is now consisting of 25 stations in operation. We are planning to deploy in the soon future 8 additional stations, for which we can track multi-GNSS observations. And in particular for Galileo, but also for the other GNSS processing, we combine the station together with the network provided by the IGS in order to have a very good distribution, a very good quality of tracking and geometry of the network to do POD. And now I will show you here some pictures in this slide and the next ones. I will show you some pictures of the results of our continuously improvement in mainly in the dynamical modeling of the satellite. I don't want to go too much in detail, so these figures that you can see here are all publicly available, were presented last year at the International Colloquium in Sofia. And this was the paper on ESA non-gravitational force modeling for 1 centimeter orbit determination accuracy of Galileo spacecraft that was generated by and produced by the Navigation Support Office, in particular by my colleague Florian Dilsner. And here you have an overview of the SLR residuals as a function of the Earth probe sun angle and 4 different models. And you can see the incremental improvement in the performance of the different models moving from the top left side to the bottom right side. So these are different models that we applied over time, and we compare the quality of them. And you can see that every time we have a new model and we validate a new model, the signal in the residuals of the SLR are getting smaller. The signal is being actually almost removed. The bias is being removed, and further on, even the sigma is being reduced significantly. So this is just an explanation of what we do here for the FOC. The IOV Galileo satellite is performing very similarly to the performance that you can see in this slide. And this is just to give you an incremental view of the performance of the different models. This is also possible to see here, the various effects of the various models and the continuous decrement in the different type of errors in the orbits. And I'm showing here on the left-hand side, I'm showing you the orbital overlaps in millimeters. So the different, the midnight point of subsequent arcs, daily arcs for different models. And you can see that in the 3D, so the last column on the first plot, for example, you can see that the performance is improving, significantly reducing the orbital overlaps error for the different models. And in the middle and the right-hand side figures, you can see the orbital predictions, respectively, for 1 day and 14 days. Note that the scale is different between all these plots. So, and also here you can see the incremental improvement of the different models that that can bring enhanced modeling on our side. And I refer you again to the paper that was presented last year in the International Colloquium if you want to see more and have more details. This is instead a figure that gives you an idea of the incremental performance of the modeling and of the performance of the Galileo constellation over time, ranging from the early stages of 2014 to almost nowadays to the end of 2022. And you see here that in dark blue, you have the orbital overlaps that is decreasing over time, and in bright blue, you see the number of satellites that is increasing over time. And you see that with time, the error that we have in these orbital overlaps, the inaccuracies we have here, is progressively decreasing thanks to the improved models that we have, thanks to the increased number of satellites, and thanks to the tracking of the GNSS network stations that we are using as well. And here I would like to give you simply an overview of what of how our Galileo products, in particular, again, the orbital overlaps, compared to the other constellation. Here in ESOC, in the Navigation Support Office, we are performing the multi-GNSS precise orbit determination, including all GNSS constellations. Unfortunately, QZSS is not included in this graphics, but we are processing that as well. And you can see that Galileo, despite this very high area to mass ratio that I showed you before, is performing very similar to GPS, and we believe the quality of our orbits is pretty good. Also, as it was validated via SLR and all the figure of merits relative to POD. So here in the Navigation Support Office at ESA ESOC, we are working on continuously enhancing the quality and performance of Galileo and the other GNSS products. We are actively contributing with our products for Galileo, GPS, and GLONASS to the IGS, publishing our data to IGS and providing support if needed. And we are also offering multi-GNSS products encompassing all constellations. And you can find all our products in our website here under the product sections. Furthermore, we also released an additional page where we inform about the latest updates and communications. So you can find here the link here under important notices and announcements, where we announce the release of new products or changes in the products and regarding GNSS, but not only regarding GNSS, for example, Earth orientation parameters or other products that we generate here. And let me state at the end of this presentation one concept that was already highlighted by my colleagues before me. Here at the Navigation Support Office, we are also embracing the Galileo measured phase center offset and phase center variations from the public metadata following the upgrade to the ATRF 2020 realization. We believe this is a more realistic interpretation of the physical characteristics of the satellite, which will allow to have a more accurate set of products and the scale of the reference frame. And this brings it to the conclusion of my presentation, and many thanks everybody for staying with us the entire meeting today.
Excellent. So thank you very much, Francesco. I think this also will probably, there are some questions related to the presentation.